Hello everyone. Today we will going to see some practice questions from the topic electrochemistry, and this is part 7. Let's start. Disclaimer which says the images used in our slide deck are for educational purposes only. We respect the intellectual property rights of original creators and owners of these images. If you are the owner of any of images used in this deck and have any concerns or issues, please contact us at sathee@iitk.ac.in and we shall remove the images. So this is the index slides and we will going to see practice questions from question number 47 to question number 54. Let's start with the question number 47. If lambda infinity equivalent of NaCl, lambda infinity equivalent of KCl, and lambda infinity equivalent of K2SO4 are 123.7, 147.0, and 152.1 ohm inverse centimeter square equivalent inverse, then lambda infinity equivalent of Na2SO4 would be. So we have given the lambda infinity equivalent value for the 3 compounds, and we have asked the lambda infinity equivalent value for the Na2SO4. Options are 128.8 ohm inverse centimeter equivalent inverse, 257.6 ohm inverse centimeter square equivalent inverse, 105.5 ohm inverse centimeter square equivalent inverse, or 118 ohm inverse centimeter square equivalent inverse. You have 10 seconds to solve this question. After that, we will see the answer. Okay. So this is the correct answer. That is option A, 105.5 ohm inverse centimeter square equivalent inverse. So we know that according to the Kohlrausch law, we can write the lambda equivalent infinity for any compound as the sum of their ionic lambda infinity equivalent value, right? So by that formula or by that concept, we can write the lambda equivalent infinity value for the Na2SO4 as equal to twice of lambda infinity equivalent of NaCl plus lambda infinity equivalent of K2SO4 minus twice of lambda infinity equivalent of KCl. Okay. So let's you have the values, just put it here. So it will be twice of 123.7 plus 152.1 minus 2 times 147.0 ohm inverse centimeter square equivalent inverse, and on solving it we have the lambda equivalent infinity value for the Na2SO4, which is 105.5 ohm inverse centimeter square equivalent inverse. Okay, so this is the final answer, and thus option A is the correct answer. Okay, let's move to the next question. Question number 48. A gas X at 1 atmosphere is bubbled through a solution containing a mixture of 1 molar Y negative and 1 molar Z negative at 25 degrees Celsius. If the order of reduction potentials is this, that is most for the Z, then Y, then least for the X. Okay, concentration is same for the Y and Z, that is 1 molar, and X is a gas at 1 atmosphere. So we have given the reduction potentials order for these three. Then which is true among the options, you have to tell. Options are Y will oxidize X and not Z, Y will oxidize Z and not X, Y will oxidize both X and Y, or Y will reduce both X and Y. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. So the correct answer is option A, that is Y will oxidize X and not Z. Because we have given the order for the reduction potentials of Z, Y and X. So you can see that the reduction potential value is highest for Z. That means its reducing power is least, right? And oxidizing power is most. So greater the reduction potential, stronger is the oxidizing agent. And we have asked about the oxidation in the options. So if you see, the same order is for the oxidizing power for these X, Y, and Z, right? So that means Z will oxidize the most, and then Y, and then X. That means Y will oxidize X and not Z, because Y is stronger oxidizing agent according to the order than X, but weaker than Z, right? Y is stronger oxidizing than X, but it is weaker oxidizing agent than Z, and that's why Y cannot oxidize Z, but it cannot oxidize X according to the order given in the question. Thus, option A is the correct answer. That is, Y will oxidize X and not Z. Okay, let's move to the next question. Question number 49. The equivalent conductances of two strong electrolytes at infinite dilution in H2, where ions move freely through a solution at 25 degrees Celsius, are given below. So we have given the equivalent conductance value at infinite dilution. Lambda naught for CH3CONA is 91 Simon centimeter square per equivalent, and lambda naught for HCl is 426.2 Simon centimeter square per equivalent. We have given these two values. Now, what additional information or quantity one needs to calculate lambda naught of an aqueous solution of acetic acid CH3COOH? So if you want to or need to calculate the lambda naught of acetic acid, what information, extra information you need other than these two values? Options are lambda naught of NaCl, lambda naught of CH3COOK, the limiting equivalent conductance of H positive, that is this much, lambda naught of H positive, or lambda naught of chloroacetic acid, that is ClCH2COH. So you have to choose one of the options. That is the extra or additional information you need to calculate the lambda naught of acetic acid. So you have 10 seconds to solve this question. After that, we will see what will be the correct answer. Okay, let's see. The correct answer is option A, that is lambda naught of NaCl. So molar conductivity of aqueous acetic acid, if you write, can be calculated from Kohlrausch law, which is equals to lambda naught of CH3COH acetic acid is equals to lambda naught of CH3CONA plus lambda naught of HCl minus lambda naught of NaCl, because for the CH3CONA it will come as CH3CO negative plus lambda naught of Na positive, right? For the lambda naught of HCl, it will be equal to lambda naught of H positive plus lambda naught of Cl negative. But we need lambda naught of CH3CO negative plus H positive, which comes from here and here. Now what about Na and Cl? So we have to subtract the lambda naught value for Na positive and Cl negative, which is equals to the lambda naught value for NaCl, right? So we subtracted from it, and hence it will be equal to lambda naught for acetic acid. Hence, for determining the molar conductivity of CH3COH solution, lambda naught of NaCl is required other than these two values. Okay, thus our option A is the correct answer. Okay, let's move to the next question. Question number 50. The rusting of iron takes place as follows: 2H positive plus 2 electron plus half of O2, giving us H2 in the liquid. E naught for this reaction is 1.23 volt. Fe2 positive plus 2 electron giving us iron solid. E naught for this equation is minus 0.44 volt. So this is the reactions or equations happening during the rusting of iron. We have to calculate the del G naught for the net process. Options are minus 322 kilojoule per mole, minus 161 kilojoule per mole, minus 152 kilojoule per mole, or minus 76 kilojoule per mole. You have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see the correct answer. The correct answer is option A, that is minus 322 kilojoule per mole. So the reaction is Fe giving us Fe2 positive plus 2 electron, oxidation of iron. E naught for this process is positive 0.44. This equation we have given in the question also, but it is in reverse form. So we just write the Fe in left hand side and Fe2 positive plus 2 electron on the right hand side. So E naught will also get reversed. That means minus will become plus. And del G1 naught for this equation will be minus N E naught F. Let's put the value. N is 2. 2 electrons are losing. E naught value is 0.44 for this process. F is F, which is a constant. Now for the second reaction, which is 2H positive plus 2 electron plus half of O2 reduction process, giving us H2O. E naught for this process is given in the question also, 1.23 volt. Now del G naught 2 for this equation will be minus NFE. So minus N is 2, F is F, to E naught is 1.23. So this is this. So G1 we have, G2 we have. Now we have to calculate the G naught for the net process. Net process means combining these two. So what we will do, the net reaction we write, which is Fe plus 2H positive plus half of O2, giving us Fe2 positive plus H2O. And the del G naught 3 for the net reaction will be del G naught 1 plus del G naught 2. The sum of the half cells reaction del G. Okay. So del G1 is this much and del G2 naught is this much. F is common. Let's solve this. It will be minus 0.88 and this will be minus 2.46, which will be equal to minus 3.34 times F. And F, put the value. So 1 Faraday will be 96500. It will be minus 3.34 times 96500 joule. And this is in the kilojoule. We convert it in the kilojoule and it will be minus 322.31 kilojoule per mole, which is equivalent to, you can write it as minus 322 kilojoule per mole, right? And thus which option is matching it? A option. Thus our A option is the correct answer. Okay. Now let's see the next question. Question number 51. Standard electrode potential data are useful for understanding the suitability of an oxidant in a redox titration. Some half cells reaction and their standard potentials are given below. You can see some half cell reaction is given. MnO4 negative plus 8H positive plus 5 electron, giving us Mn2 positive plus 4H2O. E naught is given for this. Cr2O72 negative plus 14H positive plus 6 electron, giving us 2Cr3 positive plus 7H2O. E naught is again given for this half cell reaction. Fe3 positive plus electron, giving us Fe2 positive, and E naught for this reaction is also given. Cl2 plus 2 electron, giving us 2Cl minus. E naught for this reaction is also given. Okay, so we have given the half cell reactions and their standard electrode potentials. We have to identify the incorrect statement regarding the quantitative estimation of gaseous FeNO3 whole twice from the options. And options are MnO4 negative can be used in aqueous HCl. Cr2O72 minus can be used in aqueous HCl. MnO4 negative can be used in aqueous H2SO4, or Cr2O72 negative can be used in aqueous H2SO4. You have to choose the incorrect statement. So you have 10 seconds to solve this question. After that, we will see the correct answer. Okay. Let's see. The correct answer is option A, that is MnO4 negative can be used in aqueous HCl. This is the incorrect statement we have. So the reaction between MnO4 negative and HCl may be represented as follows. 2MnO4 minus plus 16H plus 10Cl minus, giving us 2Mn2 positive plus 8H2O plus 5Cl2. This is the reaction between MnO4 minus and HCl. Now, on the basis of this reaction, following electrochemical cell will be represented, which is this: platinum Cl minus to Cl2, salt bridge MnO4 minus to Mn2 positive. Now we know that E naught of cell, since E naught of cell is equals to E naught of cathode minus E naught of anode, right? From the given data, E naught of cell, if we want to find out for this cell, it will be 1.51 minus 1.40, cathode minus anode, reduction minus oxidation. It is equals to 0.11 volt, and you can see that the E naught of cell is positive, right? That means if you see the del G is minus and Fe. E is positive, so del G will be negative. Hence, del G is negative. Thus, above cell reaction is feasible, right? But MnO4 negative ion can oxidize Fe2 positive to Fe3 positive and Cl negative to Cl2 in the aqueous medium also. Okay. Therefore, for quantitative estimation of aqueous FeNO3 whole twice, it is not a suitable reagent, MnO4 negative. Okay. But it is given that MnO4 can be used in aqueous HCl, so this is wrong, incorrect statement. And thus option A is the correct answer. Okay. Let's move to the next question, question number 52. The cell zinc 2 positive 1 molar, salt bridge copper 2 positive 1 molar copper. E naught of cell for this is 1.1 volt. The cell was allowed to be completely discharged at 298 Kelvin. The relative concentration of zinc 2 positive to the copper 2 positive, that is this much, will be. Options are antilog 24.08, 37.2, 10 to the power 37.2 or 9.65 times 10 to the power 4. You have 10 seconds to solve this question. After that, we will see the correct answer. Okay, let's see. The correct answer is option C, that is 10 to the power 37.2. So cell is completely discharged. It is given in the question. It means that equilibrium gets established and E cell becomes 0 at equilibrium. So for this cell, the cell reaction will be zinc plus copper 2 positive, equilibrium zinc 2 positive plus copper, right? And if you want to find out the equilibrium constant for this reaction, it will be zinc 2 positive concentration divided by the copper 2 positive concentration, product upon reactant, right? And we have asked this value, this much, how much it will be. So we know that according to Nernst equation, E cell is equals to E naught of cell minus 0.0591 upon N log K equivalent. We have equilibrium, so E cell will become 0, E naught cell will become equal to this much. And let's put the value. E naught cell we have 1.1 is equals to 0.0591 upon N is 2, because 2 electrons are exchanging. Now log K equivalent. Log K equivalent we just find out, which is this, right? So on equating this into this equation, it will become 2 times 1.10, that is 2.20 upon 0.591 is equals to log K equivalent. So K equivalent will become NT log of 2.20 upon 0.0591, right? That means on dividing this, we have NT log of 37.2, or you can write 10 to the power 37.2. Okay, this is our final answer, and thus our option C is the correct answer. Okay, let's move to the next question, question number 53. How long should water be electrolyzed by passing through 100 ampere current so that oxygen released can completely burn 27.66 gram of diborane? Atomic weight of boron is given, that is 10.8 unit. Options are 6.5, 6.4 hour, 0.8 hour, 3.2 hour, or 1.6 hour. So you have 10 seconds to solve this question. After that, we will see the answer. Okay, let's see. The correct answer is option C, that is 3.2 hour. So it is given that I, or current, is equals to 100 ampere, and also diborane, the mass of diborane is given as 27.66, which is burnt. So molecular mass of B2H6 will be 10.8 times 2 plus 6, which is 27.66. And number of moles of B2H6, if we want to find out, it will be given mass upon molar mass. So given mass is 27.66 divided by molecular mass, which is 27.66. So number of moles will be 1. Now consider this equation, which is happening in the question, that B2H6 plus 3O2 giving us B2O3 diborane plus 3H2. Okay. So what we will do, from the equation, we can interpret that 3 moles of oxygen is required to bond 1 mole of B2H6 completely, or you can say 27.6 gram completely. You can see here also, right? 3 moles of O2 is required to burn 1 mole of diborane. Also consider that the electrolysis reaction of water, that is H2O giving us 2H positive plus O2 negative, involve these two processes. 2H positive plus 2 electron at the cathode give us 2H and it will release H2. Whereas O2 negative adds 2 electron at anode, become oxygen, 2 such atoms, and release as O2. From the above equation, it can be easily interpreted that in the electrolysis process of water, for the production of 1 mole of oxygen from 1 mole of H2O at anode, 4 moles of electrons are required. 2 here, 2 here, right? And likewise, for the production of 3 moles of O2, 12 mole of electron will be required, because 1 mole oxygen needs 4 mole of electron. So 3 mole of oxygen need 12 moles of electron, 3 times 4. So total amount of charge required to produce 3 moles of oxygen will be 12 times Faraday, that is 12 into 9650. Okay. Now we know that Q is equals to current into time. So Q is will be 12 times Faraday is equals to I is 100 ampere times T. T we have to find out. So this is only the variable T here. So we find the T in the hours, which is equals to 3.2 hours. This is our final answer. And thus our option C is the correct answer. Okay. Now let's move to the next question. Question number 54. Given the data at 25 degrees Celsius, Ag plus I negative giving us silver iodide plus electron, E naught for this equation is this much. Ag giving us Ag positive plus electron, E naught for this process is this much. We have asked that what is the value of log Ksp for the AgI molecule. And we have also given that 2.303 RT by F, take this is equals to 0.059 volt. And we have asked the log Ksp value. Options are minus 8.12, 8.612, 37.83 or minus 16.14. You have 10 seconds to solve this question. After that, we will see the answer. Okay. Let's see. The correct answer is option D, that is minus 16.14. So what we do, we just write the reverse of this much reaction. So E naught will also get reversed, plus become negative, and we take this reaction as it is, and E naught will also be as it is. We just add them, so it will be AgI giving us Ag positive plus I negative, and E naught we also add them, it will be minus 0.952. Now we have to find out the log Ksp, so we use the Nernst equation. And we know that del G naught is equals to del G naught 1 plus del G naught 2, or E naught is equals to E naught 1 plus E naught 2. Right? So we use the E naught of cell value, which is 0.059 by N log Ksp, because the net reaction is at equilibrium, so E cell will become 0, E naught cell will become equal to this. E naught cell we know, which is minus 0.952, and N we have is equals to 1, so we just put the values and solve it. So log KSP is minus 0.952 divided by this 0.059, and it is coming out as minus 16.14. So log KSP is equals to minus 16.14, and thus our option D is the correct answer. Okay. Thank you.